Generators have multiple poles, don't they? Some of them be 2, 4, 6, and 8. Does anybody know why 6-pole generators were the most popular? Originally, when steam engines were running, we put generators on them. Steam engines run at a certain RPM, about 1200 RPM. And it turns out that a 6-pole generator is just right for generating either AC or DC, but AC especially 60 cycle. So the steam engine at its maximum RPM was just about right for a 6-pole. So that's why there were so many 6-poles to start with. Okay, 60 cycle also was determined to be the best. Now it's not. We know that higher frequency would be better, but it all had to do with the speed of the steam engine at that time. So just a little note. Okay. All right. So alternators. Let's talk about alternators. Now, even your little generating plants now, the ones that you can use for a campsite and that, are usually alternators, and they put out AC or they can put out DC, and if put out DC, they fake it is what they do. They just rectify it, okay? So let's talk about the one in the car, okay? So in the car physically, if you've ever taken one apart, you know that the rotor has little fingers on it, and they interlace back to front. So the front ones have fingers, and then the back ones have fingers, and they mesh together. You guys have had them apart that far, I'll bet. Okay. What's in between those fingers? Wire. Yeah, coil of wire. And there's one brush, isn't there? And that brush touches a commutator that turns, and that's the field. You energize that brush with 12 volts. That causes that field, because it's grounded on the other side, okay? That causes that field to energize in between those fingers, and they wound it like this, so we have a north and we have a south. So now we have fingers that are together, south, north, south, north, south, north, okay? So we rotate that, and the outer stator is set up such that it has coils all the way around. There's your coils, okay? It's 3-phase, by the way. The alternator in your car is 3-phase, okay? And when those rotate by, they move the electrons in the coils, okay? So what we end up with is we end up with a 3-phase generator. So we have 3 terminals coming out for the 3-phase, okay? Now, we need to do something with that. So what we do is we rectify that. We send it through a rectifier, and when it comes out, we get plus and minus 12 volt. Now, we still have that ripple at the 12 volt. Oops. I should write 12 volt better. And the battery is what smooths it out, okay? Make sense? And we're actually going to look at the diodes for the rectifier block there. When we get to diodes, we will actually talk about that. I don't want to go into it right now. Trust me, it's just a 3-phase rectifier, and then we'll actually look at the diodes. Okay, good. Okay. So that's how the alternator does it. Okay. And generators, AC generators, of course, they're 2, 4, 6 pole. They got a motor on them, and you start them up, and you have, some of them are 3-phase. You don't see very many 3-phase generators. They're pretty big usually. But all the little guys are just alternators with a motor on them. And they give you single phase because they're wound such that they will give you single phase. I have seen an awful lot of alternators that have on the rotor diodes, and they pick up the output of the stator and it goes straight back in and is rectified and energizes the field. And the rectifiers are right on the rotor. They rotate right on the rotor. I have an old AC, 120 volt AC wind charger that sits up on about a 40 or 50 foot tower. And it actually has a little generator behind the original generator. And that little generator energizes the field for the big generator, which is kind of interesting. Now, we got rid of that problem by doing what? All motors forever and ever had rotors and stators, and one of them was energized and the other one turned. DC motors energize the fields on the outside, the stator, apply a voltage to the rotor, and it had brushes and it would run, right? So up to a point, all of our motors were that way. And then something happened and our motors got smaller and way more powerful. Brushless. My phone's doing that thing. Brushless, yes, but how?
Do you use electronic timing?
No, I'm not looking for that. How'd they make them brushless? Why? What happened? We discovered something or built something that was way better, and it allowed us to make brushless motors of all kinds and generators. What was it? Super magnets. When iridium magnets and the light came along, we were able to replace the field with those magnets, because we had to energize that field up to that point in time. That's what it took. A lot of magnetism to make it all work, right? When super magnets came along, strong magnets came along, we could replace that field with a strong magnet. Stepper motors, generators, DC motors. We have DC motors now for bicycles and the like, and for whatever little cars. Permanent magnet. Powerful motors, very powerful motors. And they have a magnet for in the rotor or in the stator. Stepper motors all use magnets now in the rotor, and then they just step around so many steps, and they got very, very powerful magnets in those rotors. Okay. We have linear motors, even like in hard drives, that move the heads back and forth, and they use super magnets to do that. And the coils are in between the magnets, and they just simply change the current and voltage on the coil, and it causes it to move back and forth. So, and polarity. Okay. So, but our alternators in our cars are still energized with a field. Why is that? What is wrong with a super magnet in a generator? What does it cause that we can't deal with in a car? How do you regulate the voltage? So the car engine, give me a variation in a car engine. They start at what, about 800 RPM and they idle? And let's say they go to, well, it will part at 4,000, most of them I suppose, but if you have a really good car, well, what's about the maximum a car can run at? 3,200, 2,800, something like that. So let's say 2,800. So we're going from 800 to 2,800. So we changed 2,000 RPM. On the alternator, we changed that RPM, right? What happens to the alternator if the field is the same throughout that 2,000? Well, at 800, it's not putting a whole lot of energy in the alternator, so it's charging along, say, at, let's say, a couple amp, right? And so we leave the stop sign and we rev up before we shift, and it goes to 2,000 RPM. The alternator is now putting out, well, 800. How many times more is 2,000? 2.5 times. So now we're putting out, well, actually it's not linear. Turns out that it could be as much as 30 amp. So we went from 2 amp to 30 amp. What do we do with that? If it's a permanent magnet, we can't change it, can we? The regulator changes the field in the alternator so that it stays at 2 amp because the battery's charged and we're not going to blow our battery up. If the alternator is overcharging because the regulator is bad, what happens to the battery? It boils and it goes away, right? And you buy a new battery. And that one boils and goes away. You buy another one and somebody says, you know, maybe it's something else, not the battery, you know, after the third or fourth one usually. Somebody says, hey, I think we might have a bad regulator. Now, regulators exist in the back of alternators or they exist on the side. I think most of them are in the alternator now and they just stay in the alternator. But there used to be a little box on the side with some, and you could adjust them. They were really cool. So, but they're a real pain to adjust. So, okay, so we put in a regulator which changes the field so that it doesn't overcharge our battery. If you have a permanent magnet in there, how do you do that? You don't. Not unless you can regulate the output, which is really tough to do. Okay, there are some ways to do that, but it turns out that it's so much easier to just put a coil of wire in there, put a regulator in the back of the alternator. That's why every car sitting out here has a regulator in it somewhere, and it does not have a permanent magnet alternator.